this video, we're going to cover section 6.4. And so all we're really going to be doing is looking at a very specific problem type. This could have been combined with our inverse trig function in our inverse trig function section in chapter 5. But we have it separate here because we've been working more with right triangles here in chapter 6, and this is going to require us to sketch a right triangle in order to do this question. Okay, and so we're going to have 4 of these, and what we're going to see is in all of these, you have some trig function with an inverse trig function getting plugged inside of it. And so is what the trick's always going to be is we're going to let that inverse trig function be equal to some angle. And the reason we're going to be able to sketch a triangle is this means then that whatever that angle theta is that cosine inverse is giving us, well, it should also be true then that cosine of that angle is equal to minus 1/4. Okay. And this up here, we could think about as being our adjacent side. And this here is our hypotenuse, right? Adjacent over hypotenuse when we're working with cosine. But here's the next thing, is we were using cosine inverse to get this angle theta. Okay? And so cosine inverse can only give you angles in between 0 and pi. And if we're taking cosine inverse of something positive, that'll give us an angle over here in quadrant 1, and cosine inverse of something negative will give us an angle over here in quadrant 2. Okay? And this is just simply because the x values on the unit circle in quadrant 2 are negative. So this is what we're looking for here. Okay? Some angle over here. So we can go in here and we can sketch ourselves in a right triangle. Why don't we go ahead and do that? And so this right here is going to be our angle theta. Okay. And inside here will be our reference angle. And if I want to, I can maybe make it clear that what the side lengths are of this triangle. Just going to put in some dotted lines here to make it clear exactly what we're focusing on here. All right, and you can see over here we wrote adjacent and hypotenuse. So is what I'm going to do is over here on the adjacent side, I'm going to put a 1. And for the hypotenuse, I'll put a 4. Okay, right, adjacent over hypotenuse. Now, I'm going to need this side over here, okay, this opposite side. Well, we could use our Pythagorean theorem to find that. So I could take, we'll just call that maybe y. So we have 1 squared plus y squared should be equal to the hypotenuse squared, and the hypotenuse was 4. So this means that we get y squared is equal to 16 minus 1, which is 15. And so then y is just equal to the square root of 15. And we can go and we can write that in here. There we go. And so we've actually done all of the hard work right here in drawing this picture. Okay. So it may not be clear yet how this is going to help us, but here's the idea. Is we started off with this, tangent of cosine inverse of minus 1/4. And is what we said is, let's just let that cosine inverse of minus 1/4, let's just let that be theta. So now we have a new problem. Rather than finding tangent of cosine inverse of minus 1/4, I'll just use my picture over here on the left to find tangent of theta. And so one thing I do need to do when I'm using this technique with the reference angle is I need to know whether or not tangent is going to be positive or negative over here in quadrant two. And well, in quadrant two, the x's are negative, the y's are positive. So when you do y over x, you'll get a negative. So if I want to add in some extra work, you don't have to show this step, but you could write in here, well, this is going to be equal to minus tangent of our reference angle. All right, and so if we do that, then here, I have my negative, okay, and then tangent, right, is equal to opposite over adjacent. Let's maybe write that in here. Tangent is opposite over adjacent. Or, yeah, TOA, opposite over adjacent. Okay. So if we take the opposite side here, that's this root 15. So I can write that in here. And then I want to divide by the adjacent side, which is just that 1. Okay. And then from there, well, this is just going to be equal to minus the square root of 15. And that right there is our answer. It took us a bit of work, but we did get there. Okay. And I want to show that this did work out here. So I think is what I'll have us do is maybe we'll hit and open our calculator here. I'm trying to think if whether or not it's going to matter whether we're in degrees or radians. And I do not think it's going to make a difference. So we do not need to check that here. So I'm going to type in now tangent of cosine inverse. And it was of what, minus 1 over 4. Okay. And so I'm getting this right here, which should be equal to minus the square root of 15 is what we had found. All right, and we can see that these two things have the same decimal approximation. So we know we've done this correctly. All right, let's go ahead and give another one a try. And if you want to, you can pause the video before you try it, or if you're not feeling ready, you can just watch this through. So for this one here, I'm going to have us start up the same way. I'm going to say let sine inverse of 2/3 equal theta. And I'm going to zoom us in a little more here. And is what that tells us then is that sine of theta is equal to 2/3. And remember, sine is opposite over hypotenuse. Okay. And also, let's keep in mind here, sine inverse can only give us angles in between minus pi over 2 and pi over 2. Okay. And down here, y values are negative, versus up here, they are positive. Okay. And you'll note that this is a positive number that we're looking at here. So we do want to be over here in the first quadrant. Okay. And so let's go ahead and sketch that in. There we go. And this is not only our angle theta, but it's technically our reference angle as well. Whenever we have an angle in the first quadrant, its reference angle will be that angle. Yeah. And I should be a little bit more specific about first quadrant. When I say that, I really mean angles between 0 and pi over 2. Those angles will have the same, the reference angle will be the angle themselves. Okay. So now sine of theta here is again opposite over hypotenuse. Okay. And so I have this little missing side here. And so what we could do is we could use our Pythagorean theorem. So I could maybe say x squared plus 2 squared is equal to 3 squared. And so that's going to give us a 9 minus 4, which is 5. So I have x squared is equal to 5. And so that must mean then that x is equal to the square root of 5. There we go. And then next, we can actually, again, we're kind of done with the hard part here. So is what we're going to do next is we're just going to write in what we started with, which was the secant of sine inverse of 2/3. Okay. And remember that sine inverse of 2/3, we let that equal theta. So we're changing this problem into a slightly different one. We just want to find secant of theta here now. You know? And if we're trying to find secant of theta, remember secant is the reciprocal of cosine. And cosine is adjacent over hypotenuse. So this is going to be hypotenuse over adjacent. And in this quadrant that we're in, quadrant 1, all 6 of the trig functions are positive. So I don't need to include an extra like negative up front here like I did on the last one. I just simply need to do the hypotenuse over the adjacent side. So the hypotenuse is 3. The adjacent side is root 5. And if you want to rationalize the denominator here, we could multiply the numerator and denominator by root 5. And that'll leave us with 3 root 5 over 5. All right, so there's our first two. Okay, and I mentioned that we're going to try out a total of 4 of these, so we'll have 2 more to go. But these next two, they have x's in them here now. And now all the ones that we're going to do, they're going to say assume that x is some positive number. Okay? And that is going to be an important factor here. And let's see why it's important. So I'm going to have us start off the same way. Again, we'll go ahead and we'll say let cosine inverse of 2x equal theta. Because, right, cosine inverse is going to give us some angle. Now, it's going to give us some angle in between 0 and pi. That's all cosine inverse can do. So if it's cosine inverse of a positive number, we'll end up here in between 0 and pi over 2. And if it's cosine inverse of a negative, we'll end up somewhere between pi over 2 and pi. And this is just because cosine is negative in this quadrant, cosine is positive in this quadrant. Yeah. So whenever they say this, it's what they're really telling you is that this angle that we let be equal to theta at the very beginning is going to be a quadrant 1 angle. Okay. So that part of these will be easier. When the x is involved, it's always going to be a quadrant 1 angle. If not, they'd have to say, well, then let maybe x be less than 0. And you're not going to have one where that happens. So let's go ahead and sketch in our quadrant 1 angle. There it is. And you might also remember here that this means cosine of theta is equal to 2x. Okay. Now, I could leave it like this, but remember, from here, we would always say, okay, well, cosine is adjacent over hypotenuse. Well, as of right now, it doesn't look like I have a fraction in order to say that. So what I could do is I could just say, okay, well, this is 2x over 1. And then this will be my adjacent side. And this will be my hypotenuse. Okay, so hypotenuse is 1, adjacent side is 2x. To find our missing side here, we could just use our Pythagorean theorem. Let's maybe show the work for that here on the side. So I'm going to call that side there, how about y? So I'm going to have 2x being squared. That missing side that I want to find, I'm calling it y, and I'm squaring it, equal to the hypotenuse squared. So if you square 2x, you get 4x squared. There we go. And then we have our y squared, and then 1 squared is just 1. So if I start solving this for y here, I could then subtract by 4x squared on each side. And then we are just talking about a side length here. So I'm not going to write plus or minus. I'm going to say this is equal to the positive square root of 1 minus 4x squared. So that's this missing side here. Yeah. And so once again, this is the hard part, is getting this all set up. Now we'll just start off by writing down what it was we were trying to find, which was we wanted to find sine of cosine inverse of 2x. And we have said that we're going to call cosine inverse of 2x, we're going to call that theta. And so I'm just going to use this picture here to find me sine of theta. And sine, right, is opposite over hypotenuse. Right? So my opposite side is that square root of 1 minus 4x squared. And then I want to divide this by the hypotenuse, which is just 1. So this turns out pretty nice. This just gives us the square root of 1 minus 4x squared. And that right there is our final answer for that. Let me make that a little more clear, that that 1 goes up with what's above. There we go. All right, so we just have one more of these that we're going to take a look at. Feel free to pause the video and give it a try. And I'm going to go ahead and get it started here in a second. So again, we have tangent inverse, which means that we're going to end up with an angle between minus pi over 2 and pi over 2. That negative there. Okay. Now, if we were to think about what we're going to do here next, we can figure out what quadrant we're going to be in. We should already know which one, but I want to cover it again on this one. Okay. But I'm going to say to let tangent inverse of x over 3, let that be theta. And if, or is what that tells us is that whatever angle theta is, tangent of theta should be equal to x over 3. Okay. So if x is positive, that means that this number I'm looking at here is positive. And if you think about what quadrants tangent is positive in, it's positive in quadrant 1 and in quadrant 3. Because in quadrant 1, the y's and x's are both positive. So when you do y over x, you get a positive. And down here, the x's and y's are both negative. So when you divide them, you get a positive. Now, this quadrant is not included in angles between minus pi over 2 and pi over 2. So it can't be in this quadrant. We have to be over here in quadrant 1. And so I'm going to make my sketch over here in quadrant 1 then. This will be our angle theta and our reference angle. The side, or let's write down what tangent is here again. Tangent is what? Opposite over adjacent. Okay. So my opposite side is x, my adjacent side is 3, and then the hypotenuse should just be the two legs squared and added together, and then you take the square root of that. So in other words, I'm just saying 3 squared plus x squared here. All right, and then lastly, again, this is the hard part. So we just need to write down what we started with, and we can start writing down what this is all equal to. So cosine of tangent inverse of x over 3 is equal to theta, is equal to cosine of theta. There we go. And cosine, right, is adjacent over hypotenuse. Okay. So when we do that here, take that adjacent side. The adjacent side is just 3. The hypotenuse is the square root. And I could write this in as 3 squared plus x squared, or if I prefer, 9 plus x squared. And you could rationalize this if you wanted to. On a test, I'd say don't bother. But just in case the homework is going to requires it, let's just note that if we wanted to rationalize this, we'd want to multiply here by the square root of 9 plus x squared in the numerator and in the denominator. And so in the denominator is what happens is the square root of 9 plus x squared times the square root of 9 plus x squared is just going to give us 9 plus x squared. And unfortunately, in the numerator, though, we'll still have that square root hanging around here. And it is, I'm going to make my division bar a little bit longer, and then I'll write what goes in the square root here. It's just that 9 plus x squared. And so there's our final answer if we have rationalized the denominator. Right? And so this here wraps up 6.4.